This is a revision video for the quantitative chemistry topic of limiting reactants or limiting reagents. You need to know about this for Unit 3 of AQA GCSE Chemistry or the amount of substance topic for A-level chemistry. This is quite a calculation heavy video. The limiting reactants topic involves you doing lots of calculations that you've met elsewhere in the syllabus as part of one question. By the end of the video you should be able to use symbol equations in reacting mole calculations, calculate the number of moles based on mass and MR, calculate the number of moles based on concentration and volume, calculate the number of moles based on volumes of gases, identify the limiting reactant and calculate the remaining excess reactant. To start with, we need to define these terms, limiting reactant and excess. In any chemical reaction, you will never have the exact right amount of both substances. It just won't happen. It's a bit like going to make some cakes without checking what you've got in the cupboards first and discovering you have enough eggs to make 5 cakes but only enough flour to make 4. The excess reactant is the one we have too much of. In this example it's our eggs. The limiting reactant is the one that we don't have enough of, so in this example it's our flour. The limiting reactant will always determine how much product we make. If I have enough flour for 4 cakes, it doesn't matter that I have the eggs to make 5. I can't make the 5th cake because I don't have enough flour. I will only make 4 cakes. So when you're doing a predicting yield question, you always use the limiting reactant to work that out from. At GCSE, the exam boards tend to be quite kind, and in a predicted yield question, they actually just tell you the limiting reactant and assume that the other one is in excess. When you're carrying out a reaction, you always aim so that the excess reactant is the one that's easy to remove. You've met this idea in the GCSE required practical for making a soluble salt. We add excess base because it's much easier to remove that insoluble solid at the end of the reaction than to remove excess acid would be. Before we start using mass is Mr. Mole or concentration is moles divided by volume to work out the number of moles of different reactants, we need to appreciate what the symbol equation is actually telling us. A symbol equation is a bit like a recipe. So what this equation tells me is that every 1 mole of nitrogen needs 3 moles of hydrogen to react with. And when they do react together, they will make 2 moles of ammonia. So if I know how many moles of nitrogen I have, I can use the symbol equation to work out how many moles of hydrogen I need to react with it, if they were reacting perfectly. So for the first question, I've got 5 moles of nitrogen, and I can see from my symbol equation that I've got a 1:3 ratio. So I need 3 times more moles of hydrogen. So therefore 5 moles of nitrogen would react perfectly with 15 moles of hydrogen. Hopefully that makes sense. Pause the video and write down how many moles of hydrogen will react with the moles of nitrogen in each of the questions. Hopefully that made sense and you've been able to use the symbol equation to say that this reaction is going to need 6 moles of hydrogen, 0.3 moles of hydrogen, 12 moles of hydrogen, or 0.75 moles of hydrogen. Here are some questions that might feel a little bit trickier because we now have 2 coefficients to worry about. So for every 3 moles of copper chloride, I only have 2 moles of aluminium. Really, I'm trying to work out 2/3, but the way that I do this is I divide by the coefficient of the substance I have. So I'm going to divide by 3, and then I multiply by the coefficient of the substance I'm trying to work out. So I multiply by 2. By doing this, I can work out that if I have 6 moles of copper chloride, that can react with 4 moles of aluminium. Pause the video and write down an answer to each of the remaining 4 questions. So 1.8 divided by 3 and then times by 2 is 1.2 moles, 0.3 divided by 3 and times by 2 is 0.2 moles, 1.2 moles of copper chloride will react with 0.8 moles of aluminium, and 0.45 moles of copper chloride will react with 0.3 moles of aluminium. Depending on which chemical reaction you're looking at, you may need to use different information to work out the number of moles in a different way, either from the mass or from the concentration or from the volume. So we'll look at each of these in turn. The first method that you may be using is using the mass of a chemical. So there's an equation which is mass is Mr. Mole, where Mr is really the MR, it's the relative formula mass. And we calculate the relative formula mass by adding together the relative atomic mass of each one of the atoms in a compound. So let's look now at how this would work. Let's say that we have a question which requires us to work out how many moles of glucose there are in 45 grams. So my first step is to work out the MR, or the relative formula mass, which is the mass of 1 mole of glucose. To do this, I need to add together the relative atomic masses of every atom that's in that compound. So there are 6 atoms of carbon, each with a mass of 12. There are 12 atoms of hydrogen, each with a mass of 1, and there are 6 atoms of oxygen, each with a mass of 16. So I multiply each of those together and add those up, and I get a relative formula mass of 180 grams per mole. My next step is to use the mass is Mr. Mole equation, which I've rearranged here to make moles the subject. So we're doing mass divided by MR. The mass is given in the question as 45 grams, and the MR I've just calculated as 180. So 45 divided by 180 gives me 0.25 moles. And it's entirely possible and normal for that number to be less than 1, because a mole, remember, is a bit like a million, in that it's a word that means a very big number. So it's completely normal for you to have decimals or numbers smaller than 1. Let's look at one more worked example before you have a go for yourself. In this question, we're asked to work out how many moles there are in 14.8 grams of calcium hydroxide. So again, my first step is going to be to work out the MR, the relative formula mass, and I do this by adding together those atomic masses. So I've got 1 times 40, because the calcium isn't in the brackets, so I'm only using it once, and then 2 lots of 16 and 1 for the oxygen and the hydrogen. That gives me a total relative formula mass of 74 grams per mole. Now I use that mass is Mr. Mole equation rearranged, so moles is mass divided by MR, to work out that 14.8 divided by 74 is 0.5 moles. Time for you to have a go. So one more very quick worked example and then 5 questions for you to have a go at. So 17.6 grams of methane, we need the MR first, which is going to be 16, 12 plus 4 lots of 1, and then we do mass divided by the MR to get 1.1 moles. Pause the video now and work out how many moles there are in each of the 5 following substances. For question 1, we started out with ethane, which has a relative formula mass of 30 grams per mole, and 69 divided by 30 is 2.3 moles. Then we've got some propanol, which has an MR of 60, so 42 divided by 60 is 0.7 moles. Then we've got some chloromethane with an MR of 50.5 grams per mole, which gives us a total of 1.05 moles. Then there's some ethanoic acid with an MR of 60, and that's 2.9 moles. And finally, an MR of 76.5, which gives a total of 0.55 moles. Now that you're confident working out the number of moles of a substance from its mass, we can put that information together with the molar ratios that we did to start with to work out which reactant is limiting. So let's look at this first question together. We've got 28 grams of nitrogen and 3 grams of hydrogen, and we want to know which reactant is limiting. So our first step is to work out the moles of each. So the MR of nitrogen as a gas rather than just atomically is going to be 28, and so I can do 28 divided by 28 to say that there's 1 mole of nitrogen. Then our MR for a hydrogen molecule is 2, 3 divided by 2 is 1.5 moles. Now this is where it gets a little bit tricky, because you might be looking at those numbers and thinking, well, surely the nitrogen is limiting because there's less nitrogen. However, we need to use those coefficients in the symbol equation and remember that 1 mole of nitrogen needs 3 moles of hydrogen to react with. So actually, even though there's more hydrogen, there isn't 3 times more hydrogen. So it's actually the hydrogen that's limiting. Let's look at another one. So if we look at our methane reacting with oxygen, we've got 32 grams of methane, and methane has an MR of 16. So 32 divided by 16 gives me 2 moles. And then oxygen, for the molecule of oxygen, it has an MR of 32 because it has 2 atoms in it. So 64 divided by 32 also gives me 2 moles. So there's the same number of moles of each of them, but if I look at my symbol equation, I need twice as much oxygen as methane. So actually 1 mole of methane would react with 2 moles of oxygen. And so actually the methane is in excess and the oxygen is limiting. Pause the video and have a go at doing the other 2 yourself. So in our third question, we've got hydrogen has got an MR of 2, so 1.5 divided by 2 is 0.75 moles, and then oxygen has an MR of 32, so 16 divided by 32 is 0.5 moles. We need twice as much hydrogen as oxygen based on the symbol equation, So even though there is more hydrogen, there isn't twice as much more. So it's the hydrogen that is limiting. And then finally, for our final question, sulfur dioxide has got an MR of 64. So 6.4 divided by 64 is 0.1. And oxygen, we keep saying, has got an MR of 32. So that's 0.055 moles of oxygen. And we can see from our equation that we need twice as much sulfur dioxide as we do oxygen. So even though we have more, we don't have twice as much, and so it's the sulfur dioxide that is limiting. Now, it's possible that as well as being asked to identify the limiting reactant, you might be asked to work out how much of the excess reactant is left over. So in order to do this, we're going to need to look at the limiting reactant, see how much of the excess reactant it could react with, and then do a little subtraction, and then we can use the MR to turn that back into a mass. So if we look at the first question, we've got 1.5 moles of hydrogen, and we can see that nitrogen and hydrogen react in a 1:3 ratio. So if I have 1.5 moles of hydrogen, only 0.5 moles of nitrogen will react with that. So that means I've got a leftover excess of 0.5 moles of nitrogen. And I can then multiply that by the MR of a nitrogen molecule, which was 28, to work out that I'll have 14 grams of nitrogen left over. Pause the video here and see if you can calculate what mass of the excess reactant is left in each of these reactions. Looking at question 2, we've got 2 moles of oxygen which will only be able to react with 1 mole of methane. So that means there will be 1 mole left over, and we can then multiply that by the MR, which we already worked out was 16, to say there'll be 16 grams left over. For question number 3, we've got 0.75 moles of hydrogen, which can only react with 0.375 moles of oxygen, and we've worked that out by halving 0.75. So that means that left over will be 0.125 moles, and if we multiply that by the MR of an oxygen molecule, we get 4 grams. And then finally, if we have 0.1 moles of sulfur dioxide, it can react with half that number of moles of oxygen, so 0.05, and that leaves me with an excess of 0.005 moles, and I can then multiply that by 32 to work out that there will be 0.16 grams of oxygen left over. That was one of the 3 ways that we can work out the number of moles of a reactant. And we're not going to go through the full process for every single question, but we are going to look at the other 2 ways of working out moles. So my second option is for where I have a solution. So rather than having a mass, I'm going to have a concentration and a volume. And I know that concentration is moles divided by volume, so I can rearrange this to say that moles will be concentration times by volume. Now, the thing you need to bear in mind when we're trying to work out how many moles there are in 75 centimetres cubed of 0.1 mole of hydrochloric acid is that my volume is often expressed in centimetres cubed, but it needs to be in decimetres cubed in order for this equation to work. So, to convert from centimetres cubed to decimetres cubed, I divide by 1,000, and I can then do 0.1 multiplied by 0.075 to work out there are 0.0075 moles. Here's some quick practice for you. We've got the equation up there in the top right. Don't ask me why moles is N rather than M, it just is. So moles is concentration multiplied by volume, but remembering that the volume needs to be in decimetres cubed first. So my 50 centimetres cubed becomes 0.05 decimetres cubed, and then I can do 0.2 multiplied by 0.05, which gives me 0.01 moles. Pause the video now and calculate how many moles there are in each of these 5 solutions. So, my volume for the first one can be converted to 0.075 decimetres cubed, and then by multiplying that by the concentration I get 0.0225 moles. Then we have 0.025 decimetres cubed, which gives us 0.0025 moles. Then we have 0.03 decimetres cubed, which gives us 0.012 moles, 0.2 decimetres cubed, which gives us 0.15 moles, and finally 1.2 decimetres cubed, which gives us 1.56 moles. Now we're going to go through the same process that we did with the moles that we'd worked out from masses. So for each reactant you need to work out how many moles there are, and then use the coefficients in the symbol equation to work out which one is limiting. So for my first question, 0.1 moles per decimetre cubed multiplied by 0.01, because I need to put the volume into decimetres cubed, gives me 0.001 moles of hydrochloric acid. And then because I've used exactly the same numbers for my second reactant, I also have 0.001 moles of calcium hydroxide. So I have equal numbers of moles, but actually I do still have a limiting reactant, because if I look at my symbol equation, I can see that I need twice as many moles of hydrochloric acid as of calcium hydroxide. So actually, if I have 0.001 moles of calcium hydroxide, I would need 0.002 moles of hydrochloric acid in order for them all to react, and I don't have that. So my hydrochloric acid is limiting. Pause the video here and go through the process for the remaining 3 questions. For question 2, we've worked out that 0.2 mole per decimetre cubed multiplied by 0.02, because I need to put it into decimetres cubed, gives me 0.004 moles. And if I do the same for sodium hydroxide, I have 0.010 moles. Now, you don't actually need to include the extra 0 there, but I tend to find that keeping all of my moles to the same number of decimal places helps me to sort of assess how big they are and stops me getting confused in a stressful situation. So if I then look at these numbers, I can see from my symbol equation that I need 3 times more sodium hydroxide than phosphoric acid. So my 0.004 moles of phosphoric acid would actually need 0.012 moles of sodium hydroxide to react with, and I don't have that. So the sodium hydroxide is limiting. If we move on to question 3, we've got 0.003 moles of sulfuric acid and 0.005 moles of sodium hydroxide. I need twice as many moles of sodium hydroxide, and I don't have that, so that is limiting. And then in my final example, I've got 0.004 moles of hydrochloric acid and 0.005 moles of potassium hydroxide, and actually these two do react in a 1-to-1 ratio, so the hydrochloric acid is limiting. When you're doing limiting reactant calculations with solutions, you're far less likely to be asked how much of the excess there is. You could work out how many moles are left over, but you can't meaningfully say what volume is left over or anything like that. There isn't an equivalent to working out the leftover mass, so we'll just leave that where it is for now. There's one more calculation that you need to be able to do to work out the number of moles, and this one only applies to gases. We know that at room temperature and pressure, 1 mole of a gas takes up 24 decimetres cubed. And so if we're under room temperature and room pressure, we can take the volume of any gas and divide it by 24 to work out how many moles there are. So 1.2 decimetres cubed of nitrogen is going to be 0.05 moles. If I have 300 centimetres cubed of oxygen, I first need to convert that to decimetres cubed by dividing by 1,000. So 300 divided by 1,000 is 0.3, and then 0.3 divided by 24 gives me 0.0125 moles. The identity of the gas is completely irrelevant. It doesn't matter that it's nitrogen or oxygen, because every gas takes up the same volume. Here's some quick practice. So remember, firstly, we need to convert all of these volumes to decimetres cubed, and then we divide by 24. So 36 divided by 1,000 would be 0.036, and 0.036 divided by 24 is 0.0015 moles. Pause the video and calculate the number of moles for the remaining 5 questions. So here we have 0.003 moles of sulfur dioxide, 0.0045 moles of carbon dioxide, 0.005 moles of helium, 0.000825 moles of methane, and 0.00033 moles of chlorine. Again, the identity of the gas is completely irrelevant, you just ignore it. Now, there is one final sneaky trick that it's worth you having up your sleeve. For these questions that involve gases, we could solve them in the same way that we've already been doing. We could work out the number of moles of each reactant and then compare those. And you do need to be able to do that, because the exam board could very well ask you, well, how many moles of sulfur dioxide are there in 70 centimetres cubed? But there is a sneaky trick that can save us a little bit of time. We know that each mole of any gas takes up 24 decimetres cubed at room temperature and room pressure. So therefore, if we know the ratio of moles that react, which we do because we have a symbol equation, we also know the ratio of volumes that react. If I know that 1 mole of nitrogen reacts with 3 moles of hydrogen, then I also know that 1 decimetre cubed of nitrogen reacts with 3 decimetres cubed of hydrogen, or 1 centimetre cubed of nitrogen reacts with 3 centimetres cubed of hydrogen, because that ratio is always going to hold. And so therefore, 10 centimetres cubed of nitrogen will react with 30 centimetres cubed of hydrogen. So therefore, in this instance, my nitrogen is the limiting reactant. and my hydrogen is the excess. If I look at my second question, I've got 10 centimetres cubed of methane and 15 centimetres cubed of oxygen. I could go through and work out the moles, or I could just say, well, 10 centimetres cubed of methane is going to need 20 centimetres cubed of oxygen to react with, and it hasn't got that. So therefore my oxygen is the limiting reactant. 15 centimetres cubed of oxygen is only going to react with 7.5 centimetres cubed of methane. Then if I look at question 3, I can see I've got that 2-to-1 ratio. So 30 centimetres cubed of hydrogen needs 15 centimetres cubed to react with, and it hasn't got it. So the oxygen is the limiting one. 10 times 2 tells me that only 20 centimetres cubed of hydrogen will react. And then finally, I've got 40 centimetres cubed of sulfur dioxide, which could react with 20 centimetres cubed of oxygen, but I haven't got 20 centimetres cubed of oxygen. So oxygen is limiting. And actually, out of those 40 centimetres cubed of sulfur dioxide, only 20 centimetres cubed is going to react. Now, if I go back to my numbers, I can then work out what's left over in terms of a volume of gases. If I move those numbers slightly so that you can see the original volumes that we had, we can now see that for question 1, only 30 centimetres cubed reacted, but I actually started out with 50 centimetres cubed of hydrogen. So therefore, I have an excess of 20 centimetres cubed. For question 2, only 7.5 centimetres cubed reacted out of 10, so that means 2.5 centimetres cubed is the excess. And then for question 3, I have an excess of 10 centimetres cubed, and for question 4, I have an excess of 20 centimetres cubed. If you're studying A-level where these questions come up really regularly in the multiple choice question and you want a bit more practice, there is an entire video of limiting gas calculations that you can watch. Thank you very much for watching. If you found this useful, then don't forget to like and subscribe. If you want some more practice of calculating moles using any of these 3 methods, then there are individual videos for practicing those skills.